In the previous video, I had you guys manipulate, I think, 4 different algebraic problems. So I basically gave you guys the answer, and you had to show me how I got to that answer. That is basically what trig proofs are. It's really not a long, detailed proof like it was in geometry. It's just showing your thinking process, showing your work to get to the answer. So the nice thing about the proofs, and the reason why I like them, is because the answer is already given to you. You just have to do the work for it. So to start off, I want to talk about one big giant rule that I have. So with these problems, I'm going to be giving you something equals to something else. My biggest rule is that you can only work with one side of the equation at a time. So this means that you can't divide both sides of the equation by 2 because you don't know yet if those equations are truly equal to each other. And remember that the equal sign represents a balance. It represents an equality, that those 2 things are equal to each other. Now, it doesn't matter if you start on one side and then start on the other. I usually recommend that you do pick a single side and work on it. We'll only be dealing with rare cases where you will need to work with both sides of the equation. Now, the stuff that we learned with our basic trig identities, such as sine times cosecant equaling 1, and those various items hasn't changed. The idea of when you're stuck, turn everything to sines and cosines, that hasn't changed. All that I'm doing is just giving you the answer to what you guys have already been doing. So this is what a proof looks like. So before, I would have just given you tangent x plus cotangent x and would have said simplify. And then you would have, changed everything to sines and cosines, maybe tried to find a common denominator, and then you would hope that you eventually got to some simplified answer that the teacher wanted, that I wanted. Well, with these, you know exactly what your goal is. You need to simplify this side until you get secant times cosecant. Or you need to simplify this side until you get tangent x plus cotangent x. Now, I will tell you that it is easier to get rid of plus signs and minus signs than it is to add them in. So since this one doesn't have any pluses or minuses, I'm going to start on the left-hand side. Now, I don't have any squares, so I can't use any of my Pythagorean identities. So I'm going to go back to the basic identities. I'm going to use the quotient identities, which is where tangent is equal to sine of x over cosine of x, and cotangent is equal to cosine of x over sine of x. Alright, so I don't have any squares here still, but now I did create 2 fractions. And we know from our previous assignments, from our previous knowledge, that if we have 2 fractions being added together, that we need a common denominator. Well, the common denominator between these 2 would be sine and cosine. So this cosine here is missing a sine, and the sine is missing a cosine. So I can multiply the red fraction by sine of x on the top and bottom, and multiply the blue fraction by cosine of x on the top and bottom. Alright, so let's rewrite our new fractions. So sine of x times sine of x is sine square x. And sine times cosine, well, that's just sine cosine. Alright, let's look at my blue fraction. Cosine times cosine will give me a cosine squared. And sine times cosine is just sine cosine. And now I have a common denominator. Alright, so let's combine this. And when we have a common denominator, we're combining 2 fractions, we just rewrite the numerator together. So I have sine squared x plus the cosine squared x all over sine x cosine x. So up to this point, I haven't done anything with my Pythagorean identities or really my trig identities. The only thing I did was use these here to get some fractions going. All I did was use algebra to find a common denominator and combine them into one single fraction. Now what I do notice right away is that I have a sine squared and a cosine squared being added together. It is one of our trig identities. So sine squared plus cosine squared is equal to 1. So that means that this entire thing can be replaced with 1. So that entire thing is going to become 1. So when we use our trig identities, it literally replaces it with 1. So whatever you're setting it equal to, it replaces it. See how it was sine squared plus cosine squared? And it's going to become a 1. Now in a proof, I can't just erase and put it there. I actually have to take the time to rewrite that step. So that's what I'm going to do. I'm going to write a 1 over sine x cosine x. Now remember, our goal is to get secant x times a cosecant x. And now I've gotten rid of my plus signs, so I seem to be pretty close to this. Alright, now if you don't see it already, I'm going to show you. This is actually 1 over sine x times 1 over cosine x. I'm going to separate it. You don't have to separate it in this case, but for this example, I will. So now we know that 1 over cosine is cosecant x, and 1 over sine is cosecant x, and 1 over cosine is secant x. And I believe we're getting pretty close because all I need to do is flip it around. So secant x times cosecant x is equal to secant x cosecant x. And I have proven this proof to be true. Now, sometimes you guys will see me do check marks here, like this. Other times, I will do a box, like that. Just do some symbol to symbolize that you are finished with your proof. Now, a couple of things. Technically, I should rewrite this part over and over again. I understand if you don't. Just make sure you keep your work organized so that I can follow it very easily. So you see how all my work is on the left-hand side until I had to bring this one down to the bottom. Okay? Let's do another one. Alright, so here's the next example. And once again, I have two fractions being added together. And I have set equal to something that doesn't have any fractions or addition or subtraction. So I'm going to start on the left-hand side because it's easier for me to get rid of this plus sign than it is to add it back in. So before I can start, I need a common denominator. And this problem looks a lot like our algebra problems that we had, where we had x minus 1 and x plus 1. So it shouldn't be that difficult to find a common denominator when all I really did was replace the x's with secants. Alright, so that means that this one I need to multiply by secant x minus 1. Ooh, don't have quite a lot of room to write the secant x minus 1 or the plus 1. Oh, what? Sorry, that should be a plus 1. My bad. So this denominator was missing the plus 1, so that needs to be a plus. And this denominator was missing the minus 1, so that needs to be a minus. And of course, we have to do it to the top or bottom. I just don't have a lot of room to write it on here. Alright, so my first fraction in red, well, 1 times secant x is just secant x plus 1. And my denominator is secant x minus 1, secant x plus 1. Alright, let's do my other fraction. So the top is just going to be secant x minus 1, and my denominator is secant x minus 1, secant x plus 1. Now, I notice two things here. One, I see a difference of two perfect squares. See how these are factored out? And I also know that if I suddenly have a secant squared and a 1, that I probably can look at my Pythagorean identities. Alright, so my red fraction becomes secant x plus 1, and I combine it with my green fraction, which is plus secant x minus 1. And my denominator, I'm going to go ahead and multiply that out. So since it's a difference of two perfect squares, I know I'll have the square of the first minus the square of the second number. Alright, let's clean up this numerator just a little bit. So secant plus secant is 2 secant. And 1 minus 1, well, that just disappears. So I can't do much else on the numerator. And I know changing it to cosine might help, but that would also create a fraction within a fraction. So let's leave the numerator alone for just a moment and look at the denominator. Now, I know I'm on the right track because my answer has a 2. And I already happen to find a 2 in mine as well. Alright, let's change secant squared x using our identities. And the identity that we're going to use is the 1 plus tangent squared equals secant squared. Now, this is the only identity that I know of that has a secant squared and a 1 in it. See, it has a 1 and a secant squared. But they don't quite match. So I need to edit this one, because I know this is true, to look like this one. Okay, well, I need the 1 to be negative. So let's just subtract 1 from both sides. And I would get a tangent squared x equals secant squared x minus 1. So secant squared x minus 1 is tangent squared x. Okay, that was my scratch work. Alright, well, now I'm stuck. Excuse me. I don't have anything else I can really do. So let's go back to our basics. I said that when you're stuck or in doubt, change everything to sines and cosines. So let's do that. So secant x is going to become 1 over cosine. And tangent squared x will be sine squared x over cosine squared x. And when I have two fractions being divided, I can multiply by the reciprocal. So to multiply by the reciprocal, you rewrite the first part, change the division sign to multiplication, and then you flip the denominator. So it will become cosine squared over sine squared. Alright, so let's reduce a little bit here. And this goes back to what we already learned with our basic identities. This one crosses off with one of those. And so I'm left with 2 cosine x all over sine squared x. Alright, so we're getting closer. I'm going to rewrite what our goal was here. It was 2 cotangent x, 2 secant. See, 2 cotangent x secant x. That's our goal. Now, we're pretty close, because I know that cotangent has a cosine over a sine in it, and we actually have that here. And I know that secant is actually a 1 over a cosine. Oh, nobody told me that I wrote this down wrong. Well, nobody's here to tell me that. There we go. My hope if I copy the problem right from the top to the bottom. But you guys should be able to see it clearly on your paper. I apologize for that. Alright, so I'm going to write this out slightly different, just so that you guys can visually see it. So sine squared I can write out as sine times sine, because sine times sine is sine squared. And if I group these together here, cosine over sine is cotangent. And that will leave me with a sine on the denominator, which I know turns into cosecant. So we've actually proven our identity at this point. So we can say that 2 cotangent x cosecant x is equal to 2 cotangent x cosecant x. And we have proven the proof to be true. Alright, this example. So, I like this example because it kind of goes back and relates to what you guys learned when you were doing complex and imaginary numbers. So, as a quick reminder, when you guys had imaginary numbers, we told you it was a plus bi, where this was the real part and this was the imaginary part. And then a lot of the times we had you guys multiply by the conjugate, because you would multiply the i's together and you would get that I squared is equal to a -1. So the idea of a conjugate doesn't go away. If I gave you 3 plus 2 square root 3, the conjugate of that would be 3 minus 2 square root 3. If I wanted to know what's the conjugate of x minus 1, it would be x plus 1. So the idea, if you notice, is to get a difference of two perfect squares. And the way for a difference of two perfect squares to form is by rotating the signs in the middle. So that is essentially what we want to do on this problem. Now, how do I know that? Well, for one, I don't have any squares. Everything is in terms of sines and cosines already. So there's really nothing else that I can do. Now, it doesn't matter what side you start on. I am going to start on the left-hand side. I prefer the left-hand side. So the conjugate of this, of 1 minus sine theta, is going to be 1 plus sine theta. And of course, whatever I do to the bottom, I must do to the top. Alright, so let's multiply this denominator out. So if you notice, the denominator is now a difference of two perfect squares. So on the top we have 1 plus sine theta times cosine theta. And on the bottom I have 1 minus sine squared theta. Now we actually have a good thing with what we just did. So part of our goal is to get the answer of 1 plus sine theta on the top. And look what I have on top now that I multiplied by the conjugate. I have 1 plus sine theta. But I need to get rid of this cosine here somehow. And I need to somehow make this a cosine. Oh, wait. What do we have here? I see a trig identity. I see a 1 and I see a sine squared. Where have I seen that before? So hopefully you have your Pythagorean identities out in front of you. And this is the very first Pythagorean identity I gave you guys, where sine squared plus cosine squared equals 1. So I can actually manipulate this by subtracting sine squared from both sides and get an answer of cosine squared theta equals 1 minus sine squared theta. So that means that this denominator here becomes cosine squared theta. So it was, there we go. It was 1 minus sine squared theta, and it became cosine squared theta. See that? I'm using substitution on there. But like I said in proofs, we actually have to rewrite it. Alright, well now I got rid of all the addition and subtraction that was kind of holding me back. I have this being multiplied by that, and is being divided by this beautiful thing. And ironically, since this is squared, I can cross those off. Which leaves me with 1 plus sine theta on the top and cosine theta on the bottom. And that is the answer that we were looking for. Alright. So sometimes you guys are going to have fractions. Sometimes you guys won't have any. Sometimes it's just straight up multiplying two binomials out. So on this example, I've given you guys 1 minus tangent x quantity squared. Now on this right side, I have secants mixed in with tangents. So let's figure out how we can make this left side equal the right side. I'm going to go ahead and multiply out the 1 minus tangent x. Alright, so we have 1 times 1, which is 1, minus tangent x, minus tangent x, plus tangent squared x. Alright, and the tangents here become a minus 2. So we have 1 minus 2 tangent x plus tangent squared x. Now we're getting pretty close. I mean, I needed a negative 2 tangent x, and I do have that. So we want to make sure that we keep this portion. Now, what could I do to get a secant? Well, the only numbers that I have left are the 1 and the positive tangent squared. Now, 1 plus tangent squared is an identity. And just because they're not right next to each other doesn't mean that I'm not allowed to use it. I can rearrange these terms. I can write this as 1 plus tangent squared minus 2 tangent x. And then you can see that the red portion is actually secant squared x when using our Pythagorean identity. And so I get secant squared x minus tangent squared, or tangent x, which is equal to secant squared x minus tangent x. And we have proven the proof. Alright, a few little, things to remember. One, if you see two fractions, always make sure that each fraction is already simplified. So what I mean by that is that if you have a tangent divided by a sine as one of your fractions, simplify just that fraction first. My other advice is that if you have fractions, you are most likely going to have to do a common denominator. My third piece of advice, look for your perfect squares, your difference of two perfect squares. They will show up a lot. Those are your conjugates. Alright, otherwise, I hope that this has helped you out. Please feel free to rewind and check any of the proofs that we went over.